Hi, I hope you're all going well. Today I'm going to talk to you about landslide hazards and risk. And it's a general introduction on landslide in general. So, what are we going to talk about today? I'm going to give you the lecture plan first and the learning outcomes. So, basically, this is what you need to bring home. If there is anything you're going to remember out of this, those are the different points. For that lecture plan, you're going to see that I'm going to go through different elements, and some of those are going to be seen in details in other lectures. And today we're going to give a general introduction to that. So the first thing I want you to remember now is what are landslides, what is slope stability, so how do we calculate slope stability, and you're going to have a small exercise in one of the lecture. We're going to have one set of lecture on rock avalanches that are huge mass movement. Imagine the whole mountain moving all at once. We're going to talk about volcanoes and volcanic dome collapse. I'm going to give you the example of Mount Unzen. We're going to talk about some different impacts because it's about hazards, so we're going to talk about the impact and impacts on the road and the road network, for instance. We're going to talk about also man-made landslide. So a landslide is not only something natural, human can also make landslide. And this happens quite often in garbage. Then I'm going to have one lecture on debris flow and hyperconcentrated flows. And I'm going to talk to you about one example in Indonesia, which is Mount Semeru, the lahar at Mount Semeru. So after this lecture, I want you to have a feel of different type of mass movement depending on the water involved, the speed of it, and there should be a small class exercise that will come in the next lecture. So if you look at the different landslides, you're going to see that they are divided in different types depending on whether they are fast or slow, or dry or wet, so the water content. So the water content plays a role and the speed also plays a role. So what you can see on that slide here is that you have fast and dry mass movement landslide that are called rockfalls. So usually they happen very quickly, but they don't go very far. And then you have what are called the debris avalanches. So you have a mixture of soil and rocks. They are a bit wetter than rockfall, but it's not the water that played the main role. And then if you go into the wetter type, then you have at the end the mud flow. So mud flow like lahar, debris flow are much faster, and the water plays an important role. The term mud flow here is a generic term for everything which is a mixture of sediment and water. In Japanese, there is a very specific term which is used for mud flow for a certain type of debris flow. It's not what is meant here, it's everything altogether. Now, if you look at the top of the slide, you can see that you have drier, slower event like soil creep. So it's the soil slowly moving. You have the different landslide like the slump, rotational landslide, the translational landslide, and solifluction. Those different type of landslides are important to identify first because the physics and the way we're going to model them and try to understand their risk is different depending on those different types. And to understand and talk to each other about landslide, we use actually different type of vocabulary, and this is what you have here in the anatomy of a rotational slide, where you can see actually different elements. So at the bottom you have the toe, the tip, radial cracks, the ridge, the transverse cracks, and the crown and the main scarp at the top. So I invite you to have a look at all of those by yourself and try to see what they are. Maybe you want to translate them into Japanese and understand them better. And linked to the previous slide, you have on the left side here different velocities, different type of moist, dry, and saturated landslide, and they are giving you actually some ideas of how fast and how wide those different elements move. So why do we have mass movement, and how do we quantify it? I'm not going to give you details on that, but let's say that there are different theories that look at why soil move, why landslide happen, and one of the main theories is called the Coulomb theory, or sometimes the Moore-Coulomb theory, and it uses a set of concepts, and the central one will be the angle of repose, or the friction angle, which is the angle upon which movement doesn't occur, so that if that angle is over, if you go over that angle, then the landslide will start. If the angle is like that much and then you lower that angle, no movement will occur. And that's what you see here on that slide. So that's what you see with fine sand. So fine sand, the repose angle is 35 degrees, coarse sand 40 degrees, angle and pebble 45 degrees. And if you add water to that, then your angle will change. And usually for dry sand and moist sand, the angle will be much higher. But actually, if you put too much water, then all that goes down the shed and everything slides. And there is a small explanation here. Usually I do with you a very simple experiment in the class, and we can measure those together. But this time you just have to look at the figures. And that concept can then be translated into slope stability, and that's what you have here, where the slope stability is translated and known as the safety factor. And that safety factor is the balance between the driving forces that bring the slope down and the forces that actually stop the movement. And we have usually the shear stress against the shear strength that are balanced together, as you can see in that equation here. And instead of talking to you about theories and giving you a lot of different theories from the start, I think it's best for you to learn a set of equations, sort of theories and mathematical models once you have a better understanding of the different type of landslides. And I'm giving you here one example, which is at Mount Unzen in Japan, where I work for the Kokkosho. And we look at different things together, like debris flow and the Sabo Dam, Sabo Ente at Unzen volcano. And there is another issue, which is the volcanic dome, which is at the top, that has grown so much after the eruption, or during the eruption, and that stays at the top of the mountain, that now it starts to slowly slide. And this is the volcanic dome collapse. So volcanic dome are created and then slide, and at some point can eventually collapse down the mountain. So how do we study those things? So if you look at the volcanic dome, and this is an aerial photograph taken from the drone of that volcanic dome, you can see at the top here where you can see all those rocks that protrude. This is the summit, the top of the mountain. ここへ見えるのは溶岩ドームですね。雲仙火山の溶岩ドーム。で、この溶岩ドームが生まれた時は1990年と95年代の間に。で、一つのでっかい石の部分に見えるんですけれども、実はその溶岩ドームは11回以上が残ってるかなの溶岩ドーム。そうすると溶岩ドーム一つが出てきて、で、ちょっと崩れて、後ろもう一つ出てきて、もうちょっと崩れて、で、だんだん崩れていくですね。で、一番安定がないの部分が崩れると、火砕流になるとかのもあったですね、噴火中。ですけれども、今回のラバが、そのマグマ自体はすごくネバネバしてるから、ネバネバしてるせいで、溶岩ドームは完全に崩れずに、もう噴火が終わった後にもその溶岩ドームが残ってる。で、今この溶岩ドームが安定に見えるで見えないんですけど、安定してるそうな感じのものですけど、ずっとちょっとずつ 滑っていくですね。で、そのでっかい歪んドームが滑って、で、いつか崩れる可能性もあるので、その研究もやってるですね。で、このスライドに見えてるんですけれども、神戸大学がやって、東京じゃなくて、東京大学と宮崎大学と、実は国交省と一緒にやっています。で、何をやってるですね。一つのは GB サーというものを使っている。で、GB サーが電波を使って、で、その電波の反射によって、歪んドームが1ミリとか2ミリ以下の動きでもが見えるんですね。そうすると、歪んドームの上にターゲットみたいなリフレクターがいっぱい。で、そのリフレクターを使って、このリフレクター自体どのぐらい動いてるとかで見えてる。で、その歪んドームの動きが非常に難しいですね。今回見えてる図の上にすごく速く動く部分があると全然動かない部分もあるんですよね。で、見えてるのは赤いとかピンクの色はそれは早めに動くものですね。で、その早めに動くものはやっぱりドームの下の部分とか一番下流というのところの部分が早く動いてるから、あそこの山の勾配が急ですから、山の急の勾配のところでもやっぱり動きやすいのところであるですね。で、さっき見せた安全性度FS を考えると、やっぱり急の山でその上のものが動きやすいではあるですね。で、下の図を見ると、溶岩ドームが最初に溶岩の上に生まれたんですけど、だんだん崩れていくと、動いていくと、山の堆積物の上に流れるですよね。そうすると雨が降ると、雨の水が地下水になってとか、堆積物の中に入って、で、その溶岩ドームの下にも入れるので、雨の時に非常に動きやすいものになってるですね。だから大雨で溶岩ドームが崩れたりとか動いたりの可能性もあります。で、その研究のためにこんな感じの考え方やってるですよね。だからもう目標とかのいくつかの質問とか方法を考えてでやってる。で、今回の方法を考えたのは、地中レーダーとかそういうジオリストリクとかシュミットハマーとかその地球物理の方法とこちらの測量でやってるのが UAV というかドローン測量とかレーザー測量を合わせてでその溶岩ドームの動きとかスピードとかまた測れることもにする。で、図にするのはこんな感じですよね。だからレーザーとかドローンとかいろいろ使ってで細かい動き分かった上で後でまたモデル化してでそのモデルによると、いつこの歪んだものが崩れやすいになることになるとか崩れないとかも調べることが、できるですね。で、雲仙火山が1990年と94年の間に噴火してたですね。で、その噴火の影響が火砕流があって、土石流があって、土石流も海の中にも入りましたですね。で、今回の歪んドも崩れたら海の中に入る可能性もあるので、海事科学部等の人間としては、この火山にはとても重要な部分ではないかなと思います。